Other questions? Okay. So I was talking to you guys about birefringence, and depending on what planes you look down a crystal, you can see different things. And in the past, when we were talking about crystal classes, we had crystallographic viewing directions on which we looked down a crystal. These are known as Miller planes or Miller indices. And we're going to need them when we start talking about X-ray diffraction in waves hitting atoms and changing their amplitudes and scattering. So the next spot we're going to talk about are Miller planes and Miller indices. Except I can't find my chalk. Oh, I put it there. And what it is it's a crystallographic plane of a Bravais lattice. It's denoted by a parenthesis, HKL for planes, and then it's denoted by brackets, H, K, and L for directions. Okay, H, K, and L. Oh, the brackets. Well, and planes use reciprocal space, directions use real space. Okay, what do H, K, and L, what is that for? X, Y, Z. When we're talking about lattice vectors, what are we talking about there? Yep. What were the length symbols we gave? Yep. A, B, C. 1, 2, 3. Baby, you and me, girl. It's like Scarlett's favorite song right now. Actually, no. She's all obsessed about trolls right now, but that's okay. Actually, the music's not that bad. No, CoComelon is the one that really gets me. CoComelon's scary because it's designed to get your attention. It is brainwashing. You watch kids, it hypnotizes children. It's designed to do that. All right, so planes use reciprocal space. So when you move forward in real space, you're moving backwards in reciprocal space. We'll worry about reciprocal space later. Okay, we still need to use it, but we'll worry about what it means later. For now, just think of it as a mathematical exercise. Okay, and then directions. Use direct space, it's called. Meaning if you move forward in real space, you move forward in direct space. Okay. So you may be thinking this, why are we bothered doing this? If you think about it from a material standpoint, direction matters for materials. For example, on a surface, depending on its cut, you may get reactions to happen that won't happen in other situations. Another example, I worked on these molecules called concroic acid. And I'm just being lazy here. This isn't right, so don't knock me. But it's kind of how you can think about them. We made networks of these things on top of a silver surface, and you could push electricity to cause the protons to shuffle that way, or you could push electricity this way to make the protons all shuffle that way. We were making little wires to send information. Direction matters for materials, and this behavior is known as anisotropic behavior. When we get to surfaces, when you cut a crystal differently, you get resulting different chemistries. Cutting crystals differently results in different properties. You may get less catalytic activity or more catalytic activity. Okay, the other one that you're probably dying to know is what the hell is reciprocal space? Everything's time. Actually, no, everything's waves. Everything's time, which matters on the waves. Everything's waves. That's what this class will definitely teach you, is everything's waves. It's all waves. Everything's a wave. So question, what about reciprocal space? I'm not spelling right, I believe, or whatever. Oh, okay, good, I feel good about myself. We're gonna get there. This is like, you've heard the expression, you got to learn how to crawl before you begin to walk. Reciprocal space, to really get it, is like you're going to have to run a full sprint, and then you're going to have to learn how to crawl. I don't know a good way to go about it. Everything I see on the educational side of things, there's very little things to talk about it. It's just a complex idea. I wish there was a simpler way to do it. But for now, we're just going to take it as a mathematical relationship. So we will get there. But for now, the relationship for a plane is A divided by the x-intercept is equal to h. B divided by which intercept? Yep. And what's that going to be equal to? Not h, but yep. And then finally, what about for L? Yep. Okay. We're going to draw some planes now. How are we doing on time?
12 minutes. It goes to 20. Yeah, okay.
Of these colors, which ones can you tell the most apart? Can you see those apart well? Okay, can you guys see it? Okay. No, that's why I ask. Yeah, green and red. That's like my wife. Oh, that's a nice brown car. That car's purple. And then she argues with me on what color things are. It's like, come on. It's because I've messed with her too much to the point where she doesn't believe me about anything. So.
How about the time the president of the university is handing out the key? Ooh, I'll take the green or I'll take the red one.
All right, I'm going to scramble all this stuff down. Okay. So, what we have to do, what are we looking for in this problem? Yeah, we're looking for the Miller plane. What information is important to us? Yep, all these intercepts. And then if you want to visualize this, which we are going to visualize, what's the other important thing? Cubic cell. Okay. Do we want we're going to draw the lattice in white. We'll draw the plane in blue. Does that work for people? Okay. Let's first figure out the plane. So we indicate a plane with what type of symbol? What's a plane? Brackets or parentheses? Yes. You would be surprised how many times I review a paper and they get that wrong. It's almost wrong like 90% of the time. Okay, next. We got HKL. This is, why did I write 2 over 2? There we go. That's A over 2, my bad. 2 over 2 is 1, we don't want that. Okay, so what we said the relationship is A2 is equal to H, right? Okay. So what's our plane then? 2, yep. Then what about for K? Yep. Followed by, yes. So we got the 2, 1, 1 plane.
Do you not have commas in between?
You do not indicate commas. You don't need to indicate commas. It's actually a better idea to not do it because that will confuse people in thinking you mean atomic positions. So it is best to not have commas. Yep. The other thing is once you start getting like to higher numbers, it becomes more meaningless, or you can hit another plane with it. Lily.
How come it's just the number and not the like A over 2 or B over 1?
Yeah.
Well, because you're dividing that number by.
What if it was A over some other?
A over some other variable.
It's on a graph. It has to be numbers.
Well, A is
Yeah.
constant for.
Yep.
So it's not telling us constant.
I'm just not telling you the lattice constant is all. Okay, did that answer your question, Lily, or no? Yep.
divided by x intercept is h, a divided by a over 2.
Yes.
I'm just gonna go with it.
Okay. All right.
It's just not. It's not cooking. No problem.
It's not cooking. Okay. Let's draw our unit cell. You want to give some depth to this thing. Okay. The first thing we want to do is indicate the points of the intercept. So I have seen some of your guys' drawings, and I know my drawings. You need to first clearly indicate the points where you're intercepting the x, y, and z. Okay? So, ouch. 2. Where does that, remember, this is reciprocal space. We have the intercept here. Where should I be putting a dot? Oh, we want to indicate the axes too. I'm sorry. Let's go, Joe. If I go with
Orange and yellow. And green.
red or no? Yellow. Yellow works? Okay. We have our coordinate system. We're going to start it in this bottom corner. It doesn't have to, by the way, but we're going to start it there. So we have x coming out towards us, y going to the back, z going up. Okay, now we can indicate the points where it intersects. So for the x-axis, where are we going to hit? It's at 2 over a, right? So where should I draw it along here? Right in the middle. That looks to be the middle to me. You want to indicate that with a pretty hard dot when you're drawing these, so I know you know what plane you're going with. Okay, y-axis is at b over 1 to the corner. And then z, where is z? C over 1, so, yep, the corner. Okay, now we draw a plane to connect all those points. And then we shade her in. So that means we would be viewing a plane. This isn't great because it's not a cubic one, but yeah, that's exactly what you would do. You would have to rotate it to be parallel in plane with your eyes, so you'd be kind of looking at it like this. Okay? Avogadro or Vesta is an awesome tool to use to look down planes of things. Avogadro has a plane viewing thing that you can use to look down the planes. So I would suggest to check that out for some simple cubic systems. Okay. Are we good with this one? Okay. How are we doing on time? 3 minutes? It's going to go off in a minute. I don't want to touch the other ones until next time. Is that okay with you guys? Okay. Now, the 2 other questions that we're going to answer next time are, what about when you have a plane that runs parallel to an intercept? So like it doesn't cut the z-axis at all, it just runs parallel. And then what happens when we have a negative number indicated? So like if we had a 3-bar 1, 1, what does that mean? How do we deal with that? So the other question of what do we do when it's parallel, it has a value of infinity. Any number over infinity is what? Could be approximated to be a 0. So these would be parallel to those directions. Okay, your daily problem, I'm going to make you guys draw some cubes. You're going to have to indicate different Miller planes. I will try my best to not have any zeros or negative numbers in there. If I do, just email me and say, quit being a jerk. Okay? All right. Any questions right now? Okay. This is fundamentally important to understand diffraction. So really understand what's happening here and get an idea of what those Miller planes mean, because when we start going to scattering and diffraction, the math is going to get complicated, but it can all become easy if we understand this. Okay? Practice this a lot.